The research paper explores the use of photogrammetry and 3D scanning techniques for creating accurate visual representations of physical processes in Industry 4.0 systems. By leveraging consumer-grade devices with stereo vision capabilities, the authors capture depth images of an Industry 4.0 system and process these images using 3D scanning tools to create a raw 3D model. This model is then refined in 3D modeling and rendering software for the creation of a digital twin model. The reliability of this method is demonstrated by measuring the error rate between ground truth measurements and the final 3D model, showing an overall mean error of 4.97% and a standard deviation error of 5.54%. The process involves multiple stages including camera calibration, image pair rectification, and space point coordinate calculation. The results indicate that photogrammetry using consumer-grade devices can be an efficient and cost-effective approach to creating digital twins for smart manufacturing, with the flexibility to allow for iterative improvements of the models over time. The research paper discusses the creation of a visual digital twin for the SIF 405 capping station using photogrammetry and lidar scanning. The process involves obtaining ground truth measurements, acquiring images using stereo vision cameras, processing images with Polycam, and digitally processing the output with Blender. The authors evaluate the methodology for building 3D models of the capping station, presenting experiments on measuring the accuracy of the front section, comparing scanned data with baseline measurements. The results demonstrate the effectiveness of the photogrammetry and lidar scanning approach in creating accurate 3D models. The paper highlights the importance of software tools like Polycam and Blender in enhancing the accuracy and usability of the 3D models. Additionally, the authors present a methodology for creating visualizations for smart manufacturing digital twins using consumer-grade hardware and software. They conducted 3 experiments to measure the accuracy of the digital twins' physical dimensions, achieving error rates under 8% for most parts. The paper emphasizes the importance of accurately reflecting physical systems in virtual spaces for digital twins, which can enable the replication of physical processes in a cyber-physical system.